Thank you, Neha. And thank you, Professor Kapoor, for this insightful talk. And I hope the audience really enjoyed it, which is obvious from the Q&A, the questions we have received in the Q&A box. So I will be communicating those questions to you. The first question is it possible to have CH functionalization by a nucleophilic functional group, or is it essentially only electrophilic functional groups?
You can have with the nucleophilic functional groups, depending on what groups you have on your metal. Okay, so you can actually displace ligands on your metal using nucleophilic coupling partners.
Okay, thank you for your response. The next question is, what will be the near future scope of metal-free CH functionalizations?
So metal-free CH functionalization is, I would not say it is a misnomer, but CH functionalization, essentially, if you are taking into consideration without a metal, then it would not involve a CH activation step. So many of the classical reactions, if you see, if you are actually replacing a CH group by another group, then that would still be called a CH functionalization, but it would not involve a CH activation. These days, a lot of work is being done on 3D transition metals, as well as photoredox, as well as electrochemical transformations. But nonetheless, if one has to have a CH activation with a transition metal, you would still need that particular step. So without a transition metal CH activation, it would not be properly defined.
Okay, thank you. So the next question is, could we predict isolated yield via computational studies in quinoline C3CH activation?
Could you just repeat that?
The question is, could we predict isolated yield via computational studies in the quinoline C3CH activation project?
That is difficult. That is difficult because you see, what is happening in an experiment is an outcome of several factors, because you have an isolation process that is involved, which involves a workup followed by chromatography very often. So isolated yields are an outcome of the experimental procedure. One can predict what will be the energetics of the reaction. It is difficult to predict isolated yields because that will depend on the practical hand of the experimentalist who is doing the reaction.
Right. Thank you. So the next question is, what is the stereoselective outcome of the products in the enolate-based distal functionalizations? And can these transformations be made stereoselective?
Yes, they can be made stereoselective, and currently we are working on this particular aspect. So initially we did not focus on the stereoselectivity, but now we are actually working on the enantiomer selective distal functionalization using the enolate chemistry.
All right, thank you. So the next question is, as you mentioned in slide 49, that rhodium works at C3 but ruthenium at C4. Is there any particular reason behind that?
So we did a bit of a computational studies, and I don't have those slides right now. So we found that the barrier for the C4 with the rhodium species was much higher as compared to the C3. And it preferred to go only at the C3 position.
Okay.
So experimentally, I'm not sure that we have a very good proof for this particular outcome.
Right. Thank you. We'll move to the next question. So, is it possible to activate gamma or delta sp3ch bond without transition metals?
Yes, you can do this by redox processes. You can do by H-atom abstraction. It can be done, and it has been done even in the classical way, especially with the Barton reaction. We can do this, especially in the classical, if the conformation is right, then it is possible to abstract the C5H. In fact, if you have an extended pi system, you can actually go to much longer positions also.
Okay, thank you. So next question is, what is the medical and commercial application of organometallic bone formation process?
Of which bond process?
Of organometallic bone forming processes. So the
So
medicinal
essentially,
and commercial.
essentially, when you form an organometallic species, if it is not basic and highly reactive, you can store it, and you can see whether such complexes have medical applications or pharmaceutical applications. Normally, if you are using highly basic or reactive organometallic species, these would not be compatible to live cells or pharmaceutical applications. These are useful as intermediates to achieve transformations which can build molecules which may have pharmaceutical relevance.
Thank you. We'll go to the next question. So it says, what is the driving force or the nature of the metal catalyst that dictates the selectivity for distal over proximal CAs activation?
Yeah, so I can give the answer for our cases. Like I said, depending on the catalyst that we use, whether this is covalent or it is cationic, and whether the directing group is hard or soft. Based on that, we can explain that we can use either cationic catalyst to achieve proximal functionalization or a covalent catalyst to use a distal functionalization. So interestingly, I did not describe one of the works. In one of the works, when we use palladium triflate as the catalyst, instead of palladium acetate, we end up getting the proximal functionalization. Why? Because now palladium triflate is a much harder catalyst. Triflate, because it's a hard anion, makes the palladium more cationic, because of which we get proximal functionalization rather than the distal functionalization, in spite of the species being palladium-2. In palladium acetate, we still had PD2, but palladium acetate is far more covalent as compared to palladium triflate.